All right, so here we have two tuning forks, and they're not exactly the same. So the frequency of one is slightly different. So you're going to maybe turn up your volume and listen really, really carefully. So you're going to hear one frequency, and then you're going to hear the other tuning fork, and it's going to be a little bit different. And then you're going to hear them both at the same time. So you should hear this beat frequency, wow, 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 or something like that. So let's hope it works. All right, hey, it worked, right? So did everybody hear that? When they played them two at the same time, you hear that rah, rah, or whatever. All right. All right, so that's waves, right? And they're waves interfering. So guess what? We can use what we've learned to figure out how this works. Isn't that great? So let's do it. All right, so you know sound waves are traveling waves. So you have the two equations for two traveling waves, but slightly different frequency. That's the thing. Slightly, see, so look. Omega, okay, so look at it. It's a sound wave, right? So remember, F equals ma. V equals F lambda. This is sound. It's the same, right? So that means that these guys have to be slightly different, but the product has to be this, which is constant. It's just the speed of sound, right? So what that means is that, okay, the K, remember, K is 2 pi over lambda, so the K's have to be slightly different, and omega is 2 pi f, so the frequencies are slightly different, so the omegas are slightly different. So that's what we're saying here. You have two waves, same direction, same amplitude, same, but look, slightly different wavelengths, slightly different frequencies, right? Okay, now, sorry to say this, but we're going to be kind of lazy again. All right, if you want to see how they do this, look in the book. I'm not going to show you all the steps. So we want to add this and this at x equals 0, just to make it easier. And you use all your trig and everything else, and you come up with this. Okay? So here's a 2a, right? Double the amplitude. Here's a cosine. So this ought to be really small, because the frequencies are very similar. And this is just like the average, right? So this is going to be super tiny. This is going to be like the average frequency. Okay? All right. Nice. So for whatever reason, they call this the modulated frequency, right? Because that's, again, should be super tiny. So they call this the modulated frequency, and this is the average, right? It's the definition of average. Okay. All right. Great. Now, here's a question. So this is just like some ordinary frequency, right? Whatever sound frequency, This is just an ordinary number. But this is something that's really, really small, right? Because you want this, because we're saying that these are almost similar. So the question is, what does a cosine of a small angle look like? What's the graph of a cosine with a really small angle? Or in other words, what does the graph of the cosine look like when these guys get closer and closer and closer to each other? Okay? So let's look at it. What do you say? Okay, I just said that. All right. So here's a cosine of just whatever, something, cosine t, whatever it is, I don't care, right? Cosine of t, whatever that is. And then here is cosine of 0.1 t. So you can see it's spreading, right? Okay, here is 0.01, so it's really spreading, right? And here is cosine of 0.001 t. Okay? All right. All right, so are you surprised? Of course not. Cosine of 0 is 1, right? So the cosine of something close to 0 is 1, which is exactly what this is. So that shouldn't be a big surprise. Okay, now, and of course this is just a sine, right? Just an ordinary sine. So if you take this, which is kind of, it's like a cosine really spread out or stretched out, and you multiply this thing by just an ordinary sine, you get something like this, right? You get something like that, just a stretched out sine. Okay? That's what it looks like. All right? So again, this is, I'm sorry. I was wrong. I was completely wrong in what I said. This is supposed to be your stretched out cosine. This is your ordinary sine. All right? This is your stretched out cosine. This is your ordinary sine. If you put those together, this is what you get. Okay? So if you put this, your stretched out cosine, multiply that by a normal sine, you get that. Okay? That's what you get. And you can see, here's this is, loud, soft, loud, soft, loud, soft. Okay? Right? And that's what I was trying to say. Wow, 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 right? Loud, soft, loud, soft. Okay? So here, good luck. All right. So this is from lab. We had two frequencies that were similar. Can you kind of see a beat pattern? A little bit? Here, how about that? Is that better? Can you kind of see that beat pattern? All right. Okay. Now, as shown in the textbook, okay, so there's a frequency, right? There's a frequency to this beat pattern. As shown in the book, this is the beat frequency. It's just the absolute value of the difference, right? So if you have two violins and they're just a little bit off, let's say they're 2 hertz off, you're going to hear this beat pattern rah, 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 with a frequency of 2 hertz. That's all. All right? There you go. Okay, now this is sort of interesting, I thought. I mean, we're talking about music, but it's actually more involved than just music. If the two propellers on this airplane are not precisely synchronized, the pilots and passengers will hear beats. Can you imagine being in an airplane for 8 hours, hearing this rah, 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 rah? Drive you nuts. So it's not just music, all right? It's all over the place. All right. Why is that there? I don't know. Can you stop it, please? But not